Now we're going to move on to what is really quite a bit simpler than it looks, but it's more difficult because of the math involved. And most of the people have trouble with mathematics, so I will be very clear that you will not be, when we grade these things, if you get the setup right, you'll get 90% of the credit. And if your math is a little screwy, then that's okay. We can deal with that later. And what we're talking about here is something called Kirchhoff's rules. Kirchhoff's rules are circuit situations where you cannot combine with series and parallel connections. So you can't reduce it to anything lower than it already is. Now you might look at the bottom of this and say we could combine little r2 with big R3, and I suppose that's true, but after that you're still in a pickle of a situation. And so there are certain rules that take advantage of the fact that there's a conservation of charge and a conservation of energy that help analyzing this. But what you end up doing is generating generally at least three equations and three unknowns that you have to find the result for. And that's the difficult mathematical part. So there's two specific rules. The first rule is called the junction rule, and it states the sum of all current entering a junction is equal to the sum of all the current leaving that junction. So that's the conservation of charge. The second rule is called the loop rule. The loop rule is that the algebraic sum of the changes in potential around any closed path must equal zero. So when you introduce a potential difference with a battery, all of that has to be used up by the time you finish the loop and return to the same battery. So here's an example of the junction rule. You're going into junction A here with 11 amps on I1, and this divides up to 7 amps to I2 and 4 amps to I3, so that I1 is equal to I2 plus I3. The junction rule diagrammed here is just as I've described. And here's a loop rule. It's an example. This is an example of the loop rule with two ways of looking at it. The presumption is that the flow is clockwise, and it's important to see what direction of flow you're assuming is occurring. In the top, you have what's known as a standard schema. You start out with 18 volts, and it has to be reduced to zero by the time you get back to that point. So you lose 1 volt crossing the internal resistance of 0.5 ohms. You then lose 17 volts crossing the 6 ohm resistor, and the remaining 5 volts crossing the 2.5 ohm resistor. This can also be looked in a perspective view, which sort of makes it look like a roller coaster that first jacks you up on the hill at 18 volts and you start slowly losing it. Then you go around until you get to the 6 ohm resistor and you go down a big hill, and then a little bit smaller hill once you get to the 2.5 ohm resistor. Now, this is where people get confused. In every one of these four diagrams, we're moving from A to B, okay? If you're moving from A to B, and you're going in the direction of, and that A to B is the same as the direction of current, then the I times R has a negative sign. In other words, it's a voltage drop if your direction of your loop and the current is in the same direction. Next door here, you have the direction of the loop being opposite the flow. Therefore, it's a positive IR. This is shown in top right-hand side. So on the left-hand side, the direction that you're going in your loop and the current direction is the same, so IR is negative. On the other one, A to B is in the opposite direction as the current, therefore it's plus IR. If you look at battery sources or energy sources if you go in the same direction that the flow would go. So from minus to positive, which is the direction that flow would go, and you're going that way from A to B, then it's a plus whatever the EMF is. Conversely, if you're going against the grain, against the flow, your loop is the opposite direction, then it's minus E. So each resistance and source that traverses you're traversing in your loop from A to B. And the signs depend on the direction of flow in relation to your traverse. Now, there are certain strategies that you have to undertake when you do these problems. Now, whenever there are strategies, that means that we're talking about something a little more complicated. Make sure that your diagram is clear and you've labeled your diagram with the right currents, resistances, whatever you know. Now, sometimes you have to pick a loop direction. And if you pick a loop direction for the current and the answer you end up with is negative, that means the direction you picked is wrong. It was opposite of that direction. And all you have to do is say that. And that corrects your answer. And we have a situation in our problems like that. You then, at any junction, you apply the junction rule, and then you pick a couple of loops to do the loop rule. Now, sometimes you don't have to do all the loops you can do. You just do the ones you need to get. If you have 3 unknowns and you need 3 equations, then you do 1 junction rule and 2 loop rules. That gives you 3 equations, and then you stop. Then you have to solve the simultaneous equations, and this is what challenges most of our math. And see if the answers are reasonable. Now, here's the situation we're going to do, and we are assuming the directions are as shown above. So that the fact that those are marked that way doesn't mean they're correct in terms of direction, but we're going to make that assumption as we do the problem. So let's take a look at how we would do this, given the assumptions we're doing. Now, first of all, we have a junction right here at A. So we have I1 splits off into I2 plus I3. So by junction rule, we know that I1 is equal to I2 plus I3. Now, there's 3 loops here that you could use. I'm only going to use 2 of them. There's this loop from A to B to C to D to E, back to A. There's this loop from A to E to F to G to H and back to A. And then there's also from A to B to C to D to E to F to G to H, the whole thing. I'm just going to use the first 2 that I just mentioned. So let's start at A. We're going the same direction, so that's going to be minus, and it's going to be 2.5 times I2, or 2.5 times I2. We're going in the same direction that flow would go, so that's plus 18. Again, it's going to be minus 0.5 times I2. Loop around to E here, and then we're going to go this way. And we're still going in the same direction that they're showing I1. So that's going to be minus 6 times I1. And all of that has to equal 0. So that's our first loop. Now our second loop, we're going to go this way, just for the heck of it, from A to E. So that's going to be plus 6 times I1. Down this way, E to F, again, is going to be plus 1.5 times I3. Going this way, is going to be plus 0.5 times I3. Now you don't have to do it in this direction. You could have done it in the other direction. We're going against the grain here, so that's minus 45. Loops it back up here, and we go back here, and we're done. So here's our two equations. So we can simplify each of these. We can say 18 minus 3i2 minus 6i1. And we can say 6i1 plus 2i, this is a 3 here by the way, I3 minus 45. Both of these are going to equal 0. Now what I do at this point to solve these is I use this equation. And I substitute, for this one I substitute 6i2 minus 6i3. And this one, I do the same thing, 6i2 plus 6i3 is equal, or plus 2i3 minus 45. So now we've got 18 minus 9i2 minus 6i3, and we've got 6i2 plus 8i3 minus 45. And at this point, there's a couple of ways you can do this. You can multiply this bottom one by 1.5. Now what that does is that makes this 9i2, and that goes along with this 9i2, and you can cancel those. You add them together, you end up with 18 here, and these two guys cancel each other out, and you're adding, now this is 1.5, so this is 12 minus 6, so that's minus 6i3, and 1.5 times this is 67.5. And so you end up with 6i3 is equal to 49.5, and I3 is equal to 8.25. Now if you put this back in here, any one of these, you could put this back in this top one here. So you have 18 minus 9i2 minus 6 times 8.25 equals 0. You put that in, and you're going to get a minus 3.5 for I2. Now that's not a wrong answer. All that means is that the assumption over here for I2 is incorrect. And it should be going this way. Okay? And so, which would change this equation up here, because you now know that it's this coming into and this coming into, so it's actually I2 plus I1 is equal to I3. So if this is positive 3.5, and you know that I2 plus I1 actually equals I3, that means that I1 now is going to equal 8.5 minus 3.5, 8.25 minus 3.5, or 4.75. And that's how you do it. And obviously, as you look at that, you see that the hardest part of this whole thing is doing is figuring out which direction to do. Now I'm going to finish up with a fairly quick discussion of DC amp and voltmeters, and that'll be all we talk about. when you measure the potential difference with a voltmeter, you have to put your voltmeter in parallel with the resistances with the circuit that you're involved with. Why in parallel? Well, remember that the voltage is the same in your voltmeter as it is in the circuit if they're in parallel with each other. And so that allows you to measure what the voltage is, and it will be the same as the voltage in the circuit. Conversely, if you want to measure the amperage, remember the amperage is constant throughout a circuit, so you put your amp meter in series to measure the current. You put your voltmeter in parallel, you put your amp meter in series, and actually, quite honestly, this is the most important part of this discussion that you need to remember. When you put your voltmeter in parallel, you use a very large resistance. Why do you use a very large resistance? Well, remember, the equivalent resistance is 1 over the equivalent resistance is equal to 1 over each resistance in the circuit. When you use a very large resistance, 1 over that number is an extremely small resistance, and therefore it does not change the equivalent resistance by very much. So, and the larger the voltage you're working with, the larger the resistance in your voltmeter that you have to use. Now, conversely, when you're measuring amperage, you want to make sure that you use the smallest resistance that you can use, because remember, amperage is the same throughout. So if you put too big of a resistance in there, or the other way to think about it is that the equivalent resistance is the sum, and therefore the bigger the number you put in there, the worse it is. So when you're measuring voltage, you want a big resistance. When you're measuring amperage, you want a very small resistance. And here's shows you what I'm talking about. The desired is A here. A voltmeter has to have a resistance that's much larger than, so that it does not affect the equivalent resistance involved. So you have here, if 1 over the resistance in the V there is extremely small, then the equivalent resistance is going to be very similar. But if R and the resistance within the voltmeter are about the same, then you end up with an equivalent resistance of about half that, and you don't want to have that impact. This shows you the same situation with amp meters or an amp. You want something extremely small so that the sum of A plus R is the same, or very close to the same as R, rather than two resistances that are very close together so that the sum ends up being 2R. So let's take a look at one set of problems here using the what impact the voltmeter has. And this first problem is very straightforward, and it states that what is the sensitivity of a galvanometer inside a voltmeter that has an internal resistance of 25 kiloohms on a 100 voltage scale? Well, in order to do this, it's very simple. V is equal to IR, and in this I here now is going to equal V over R. And so the sensitivity here is going to be 100 divided by 2.5 times 10 to the fourth. So the sensitivity is going to be 4 times 10 to the minus 3 amps, or 4 milliamps, which is pretty good. Now the second problem says what resistance must be placed in series with a 10 ohm galvanometer having a sensitivity of 100 microamps to allow it to be used as a voltmeter, first of all with a 100 volt, 300 volt scale, and then with a 0.300 volt scale. Well, if you start out with a V100, you know that R total is equal to big R plus little r, which is equal to V over I. And so what that means, that big R, which is what we want, is V over I minus little r, which in this case is going to equal 300, that's the scale, divided by, you've got 100 microamps, so 1 times 10 to the minus 4, minus 10, which is that other r, and you end up with a 3 times 10 to the 6th ohms. Now if you just change the scale, it's the same calculation, but now instead of 300, it's 0.3 divided by 1 times 10 to the minus 4 minus 10, which ends up being 2.99 times 10 to the third ohms.